So now we're ready to go back to this issue of the spectrochemical series. And remember what this was. This was a list. It was just a list that we were given of different ligands. And there's infinite number of ligands, and you can construct, other more exotic ligands in here in this list, but these are common ligands. And, it said that basically ligands at the bottom of the list, beginning of this list, have the weakest splitting. So for delta O or delta T, the gap between the EG and T2G, everything else kept the same, will be the smallest when you have iodine as a ligand. And when you have carbon monoxide as a ligand, you have a very big gap. Okay, so we call carbon monoxide and cyanide and nitrite. Those would be strong field ligands, big splitting, strong splitting. Okay, weak field ligands would be things like iodide, bromide, sulfide. And we really were at a loss here, and we mentioned that crystal field theory cannot explain this. Crystal field theory is just based on electrostatics. It's just based on electron-electron repulsion between ligands, the orbitals of the ligands, and the electrons on the metal. And so you would expect that more highly negatively charged ions would actually have a lot of electron-electron repulsion, right? And that neutral molecules would have much smaller. But there's no trend here. There's neutral molecules all throughout this, and there's negatively charged molecules all throughout this series as well. And we said what is missing here is bonding, right? There's bonding interactions. These different ligands all can bond differently and change the energetics of the molecular orbitals differently as a result, okay? And so in order to do that, we have to step away from crystal field theory and go to something more accurate. Go to theory that's more accurate, one that's based on quantum mechanics, right? And you know what that is, that's molecular orbital theory. So that's what we're gonna do in this video. We are going to derive very quickly here because we know how to do a lot of legwork, so we're gonna skip through a lot of it. We're gonna do NMO theory for transition metal complexes. So same ground rules apply. We're gonna choose a structure. Whatever structure we wanna start out with is fine. Then we're gonna figure out the point group. Always gotta do that first. Then you're gonna construct symmetry adapted linear combinations, SALCs. And you're gonna mix the atomic orbitals on the metal center with the SALCs of the same symmetry. Only things with the same symmetry will be able to bond. Otherwise, your overlap integral, they're orthogonal, right? And they have to have same symmetry and they have to have similar energy, right? And so what are we gonna do? Well, let's start with the octahedral ML6 complex. So that's gonna be OH point group. And for now, let's just assume that the ligands can only undergo sigma bonding. So we know that we can represent sigma bonding by vectors pointing toward the central atom. And so we ask the question, all right, what's the reducible representation that represents the sigma bonding for all of these orbitals on the ligands, right? So for identity, well, that's gonna be a value of 6, right? Because we have 6 sites, 6 ligands that we're doing sigma bonding from. Then we can do a C3, and you can choose any C3, but basically, hopefully you could get these yourself. I chose a C3 that goes through, let me just draw that here, goes through this triangular face. Okay, remember octahedrons, the oct sides, the 8 sides are triangles. So it's going through that triangular face. We're doing a C3 rotation. And so it looks like I actually did the other direction. Remember, there's symmetry operations in each class. There's a C32 here, so it doesn't really matter which one you use. But this is going to be a clockwise. V1 goes to V2. V2 would come down, swing around to V6, and V6 would go to V1 here. And similarly, there's this face that we're also going through, okay? This triangular face right there. And so all of these are going to interchange. So we're talking about here, V3 is gonna swing over to V5, or it could go to V4, it doesn't really matter, right? All these are gonna interchange. Since everything's interchanging, all 6 interchange. That's not going to give you any elements on the diagonal of the transformation matrix that are ones or negative ones. It's going to be all zeros. So our character there is going to be 0. And you can go through this for C2. C2, let's see, it looks like I chose this C2. Okay, so that's going to be a 180-degree rotation. That's going to flip V1 and V6. You can see those are interchanging. It's going to flip V2 and V5, and it's going to flip V3 and V4. So all of them again moves. The character is going to be 0. We can do C4. The easiest C4 to do is probably the one going straight down the axial ligands, V2 and V5. That's a 90-degree rotation. So V1, let's see, I did it clockwise. So V1 goes to V3. V3 is going to spin around to V4. V4 goes to V6. V6 goes to V1. But since we're spinning it along V2 and V5, none of those change. So V5 and V2 not changing, give us a 2 for our transformation matrix character. Now we have a C4 that is done twice, that's equal to C2. And so again, this is the same sort of phenomenon here. It's this, we can choose the same sort of one. V2 and V5 are going to stay the same. The other ones are just going to spin a greater quantity. V1 is going to go to V4, V3 goes to V6, and vice versa. That's going to get you a 2. Inversion, you know, everything changes, right? Something on the top goes to the bottom, so V2 and V5 flip. Something on the left goes to the right, etc. So that gets you a 0. S4 similarly is a 0 because now you've done a C4, but you flipped it. So on the C4, V2, if we define our C4 as being there, V2 and V5 didn't change, but then you did a horizontal mirror plane, right? And so that switches V2 and V5. So everything changes. An S6, that is going, again, through a triangular face, okay? And that's going to move everything around. So basically, you know, those are going to move all around. Now we get to a sigma H, and that's interesting. There's many different sigma H's we can choose because there's many principal rotation axes. Easiest one to see is right there. Sigma H is horizontal to the C4, right? And you can see that that sigma H is going to flip-flop V2 and V5, but V1, V3, V4, and V6 are going to stay the same. So that gives you 4. And then there's 6 different sigma Ds. These are moving through bonds. These are moving in between bonds, okay? And so I chose one that's interchanging V1 and V6. So I'll try to draw it here, but it's basically going through there. Okay, so V1 and V6 interchange, V3 and V5 V3 and V4, excuse me, interchange, and V2 and V5 are in that plane, right? And so again, those are the ones that don't change, so we get an order, a character of 2. So, you know, hopefully you guys can do that pretty quickly now that you've had a lot of practice on that, but then we would reduce it. And so we can reduce that, and if you do that, you can reduce it by inspection, or it's probably easier. This is a pretty complicated character table to reduce this using the reducing representation formula. And if you do that, you'll find that this representation that we just calculated transforms as A1G, EG, and T1U. And you can see if you add these up, right, 1 plus 2 plus 3, that equals 6, okay, etc. 1 plus -1 plus 0 equals 0. Okay, and you can go through, and that's how you check your answer, of course. Great, so those are our solves. So now, those are the symmetry of solves. By the way, we have 3 of them, right? A singly degenerate A1G, a doubly degenerate EG, and a triply degenerate T1U. How do we figure out what these look like? Well, we would use the projection operator, right? And so go back to the example when we did this for the AH3 solves in chapter 6, when we're going over Walsh diagrams. I trust that you'd be able to do this, or at least be able to come up with the what the first orbital looks like if you have a degenerate set. Remember, the math got kind of complicated when you have to figure out what the future sets look like. But, you know, at this point, let's not waste time trying to figure out what all the orbitals look like. We know how we can do it. It's just a bunch of math. So let me just give you the answer. Of course, the A1G is going to be the totally symmetric representation, and you'll have practice on the homework on these using projection operators. So you don't have to worry about not having enough practice. That's going to be totally symmetric, so all of these orbitals are going to be in phase. The EG looks a little funky. There's no electron density at these axial spots for this set. And then you have sort of these conical shaped nodes, okay? But basically, that's what it looks like. So you have square planar in the same sign there, and then the opposite sign for the axial ligands. And then the T1Us, you have 3 of them, and they look like this, where there's actually square planar portion of the molecule of the salt that has no electron density, and then it's just oriented a different way with opposite signs. Cool, so once you have all of that, well, you think about what's available for bonding on your metal, right? And what is available for bonding? A d orbital, an s orbital, and a p orbital. So if you're talking about a first row transition metal, you know, you can look at the periodic table and figure out what the principal quantum numbers would be for those. But this is essentially, it's going to be 4s, 3d, and 4p, right? We're just making this general here. Again, these salts were only for sigma bonding, right? We only talked about sigma bonding. And so I just kind of went ahead and I filled all this in. We know the symmetry of salts, A1G, EG, T1U. I got that from all the work we did. And these, how did I get these? I looked at the character table for octahedral, and I knew that, okay, I have an s orbital. S orbital's always totally symmetric, ones across the board, so that's symmetry A1G. I have p orbitals. Those have transformed as the functions x, y, and z for the px, py, and pz respectively. That's going to be symmetry T1U. And then I have my 5 d orbitals, and those are going to be, of course, EG and T2D. We kind of knew that from before our discussion of crystal field theory for octahedral molecules. So that's where we are. That's how I got all these EG plus T2G, A1G, and T1U. And so now we go ahead and make bonds and anti-bonding molecular orbitals between things that have the same symmetry. So we have A1G for our s orbital, A1G for our salt, bonding, anti-bonding. We have a EG that we can make bond with the salt, right? So anti-bonding, bonding. We have a T2G in the d orbital. There's no T2G salt, so that has to slide over and be non-bonding. And then we have T1U, and that has the same symmetry as 1 of 3 of the salts, so out of T1U. So those can come down, okay? And so that's what your overall diagram is gonna look like. And so, you know, a key thing to see here, you might be wondering something about the energy ordering here. The d orbitals, you know, the periodic table, you write 4s, 2, let's say 3d, 10, 4p, 6. This would be, you know, at the end, this would be a noble gas configuration, but you write it this way. We're used to filling it this way. Most of the time, we're talking about ions here, metal ions. And when you go to make an ion for various reasons, it has to do with electron screening. Actually, the d orbitals are the lower energy orbitals, the s orbitals. So the d orbitals, the s orbitals are actually higher in energy, okay? And so that's just sort of one of these things at this level we just kind of have to know, has to do with the energetics, and really you have to do quantum mechanical calculations to show why. But that's why you have the d orbitals are always going to be lower in energy than the s and the p, okay? That's just the ordering for transition metals. Then you can go and assume that you basically have, we're assuming in this case for these molecules that we have electrons in the salts. And what's very interesting is here are the orbitals that we considered in crystal field theory, right? We have the EGs and we have the T2Gs. And now you can see that the T2Gs are actually non-bonding when we consider the whole molecular orbital diagram, and the EGs are anti-bonding in this way. And so that's sort of how this, this all works. And so I pulled over 12 electrons, okay, coming from salts. So these are anti-bonding orbitals by our formulation, right? And so what is very interesting here is that, let me just clear all this ink, is that before you reach the anti-bonding orbital, you have 18 electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18. And so you may have heard of this 18 electron rule. You know, there's an 8 electron rule for Lewis structures of main group compounds. For transition metals, 18 electrons tends to be the magic number because 18 electrons is the maximum amount of electrons you can fill up with before populating these anti-bonding orbitals. Now you might be saying, well, non-bonding doesn't sound that bad. You know, what about 16 electrons or 14 electrons or maybe even 12 electrons? And the answer is yes, there are stable molecules with 12 electrons. There are stable molecules even with 20 electrons. They just tend to not be as stable, and this is why, okay? And it depends upon the specifics of the energetics of all these systems. This is a very generic MO diagram that we've tried to make. Again, this only had sigma bonding. Remember, the salts that we derived from only had sigma bonding, okay? So next, we'll talk about more in detail the 18 electron rule and how you can use this as a very simple rule to predict the stability of different molecules.